So we recently talked about the whole importance of tuning a machine. And we said that we have to do this really on a daily basis, if not twice a day, depending on the company that I work for. And these tuning files are something that I want to save, and it's something that I want to put into a folder because it gives me an idea of how dirty my instrument is getting. And I can refer back to this data to figure out where along that process did it happen. So we talked about PFTBA being used as the standard, and we said that our machine will use PFTBA to go through and look at fragmentation patterns. And these fragmentation patterns are going to be very important because that's how the machine knows if it's doing its job the proper way. All right, so now we've talked about kind of the ionization chamber. We said the electron beam comes through and the fragment will maybe become a positive charge, and now we need to know what happens in the next step. Where does it go? What happens to these positively charged pieces? All right, so before we do that, we want to talk a little more about the settings that are happening in this ion source. That's really what we're calling that because that's giving us our ions, right? Well, we've already talked about one, and one is the 70 electron volt. We said that everything has to be 70 electron volts because that's how the databases are produced, and these databases are very important. It helps us to identify the compound that we're using. So that's going to be the number one thing. We want to make sure it's set at 70, and some instruments allow me the freedom to change that number, especially if we're doing research and development type stuff. Another setting that we really didn't talk about, though, is the temperature. The temperature of this ion source box. And this temperature typically is going to be 200 degrees Celsius. Now, many times I have to kind of confirm that temperature. I want to put that temperature into the method and save it so that way when I run samples, everything's ready to go for me. So this is a temperature setting that I can change. I can crank it up a little hotter, I can lower it down a little bit more, but 200 is generally the recommended temperature that I would see with many different methods. Now, I'm going to kind of put that as a disclaimer. Check your method. The method is going to tell you the setting for the ionization temperature. You just want to make sure that it matches. Typically it is 200, but depending on what we're running and depending on the types of molecules, we might need that to be a little bit hotter. All right, now we've created this positive charge. And these positive charge, the species has to be controlled. So we can't just pump positive things through and forget about them and hope that they reach at the other end of the detector, right? We need more control here. That's the problem. We've created these things. Now, how do we make sure that we keep them in line? Well, the way that we do that, if we're working with positives, and again, remember, those are cations, and we're calling them molecular ions just to sound fancy, but these are charged compounds. And anytime we deal with charged compounds, one of the ways that we can kind of control them is using a magnet or a series of magnets. So if we can somehow embed magnets into this whole ionization chamber, then what can happen is that we can increase the number of positively charged species that are going into the system, and we can increase the electron count going out of the system and the negative pieces going out of the system. And we can even control the electron beam itself. Remember, this is an electron beam. Electrons being negative. So we are going to see magnets everywhere. Everywhere. From the time that the molecule enters the system to the time that the molecule exits the system, we are going to see magnets involved in every step along the way. All right, so first off is the electron beam. This electron beam has to be controlled. It has to go into a straight line, and this is a negative line, right? This is a negative beam of electrons. So we're going to first see a magnet that's going to be located here. And what happens is that this controls to make sure that this guy is going to be a straight line and we don't get any curvature to this line, and it goes from point A to point B and straight through there, and that is it. As long as that is doing its job the right way, the molecules are going to get slammed with the electron beam, and that's what we want. Number two, we're creating a positive charge here. So embedded into this system, think of it almost as another magnet. And I'm just going to draw it over here to the side. And I'm just going to put magnet number 2 maybe. And another magnet is going to be present to repel. It pushes away those positively charged species. All right, well, that probably means that this magnet has to be positive. So when we create these positive ions, they can kind of leave and be persuaded to leave that ionization source. Otherwise, they're just going to stick around. They have no reason to leave that box and head out of there. They're just going to be formed. So if we put in a magnet, and that magnet is positively charged, then we can repel these positively charged fragments or molecular ions out of that chamber and into the next spot of the instrument. So we're going to have a magnet there. And then once they get into this next area, and I'm just going to kind of draw this big long tunnel for now, we want to make sure that these positive pieces kind of stay in the middle, right? We don't want them to deviate their course, and we want them to come out the other end. Well, that means I probably will need a magnet down here. And that magnet's probably going to be something like a negative piece. That way, this magnet's pushing them out, and once they come out, they see that magnet, and they can kind of travel down this path and make their way toward that negative charge. In addition to that, I don't want to lose the path in this tunnel that I've drawn right here. So there's probably going to be more magnets on the top and the bottom of this guy. And these magnets are to control the position of these positive pieces. So again, we have magnets in the front end, we have magnets in the middle end, and we have magnets at the very end of the instrument. First one controls electron beams. The second one pushes the positive species out of the electron chamber. The third one controls the positive pieces in what we are going to call the tunnel, but we're going to give that a proper name in just a second. And the fourth one is basically a lure. It basically allows the positive pieces a reason, or gives them a reason, to travel down that tunnel and come out of the other end. So it promotes acceleration. There's a lot going on. I mean, this is no way like our UV vis instrument. This is really not our infrared or AA. And you've got to keep in mind that this is just the detector. This really isn't even an instrument. It's not doing any type of separation at all, which makes this even more complex because there's front end things that are going on before it even reaches to this step. All right, so I've got a picture that I would like to show you. And it looks like this from Shimatsu. So here to the left, this is the ionization source. All right, so this is where your molecule is going to come in, and your molecule is going to get slammed with an electron beam. And that's what you're seeing kind of happening right here. So this is the area that it's going to be using to create a charged species. So here's the electron beam. All right, so after these things are charged, it goes down this tunnel. And I've called it a tunnel just a few minutes ago, but the proper name to this tunnel is something that we call a quadrupole mass analyzer. A quadrupole. There's actually different versions of this now, though. Quadrupole is typically the most common, but we can make these things a little bit more complicated, a little bit fancier to get us to do the job a little bit better. But quadrupole is typically what most of the basic MS detectors are going to be using. So if I look at quad, we're going to be thinking of 4, right? So we're going to take a look at a quadrupole and we're going to see how that thing is made up and what really is that tunnel. But keep in mind, 4 is going to be a key number. All right, so these ions will zoom down this tunnel or this quadrupole, and then they'll come out the other end to the actual detector that's going to be doing the ion detection or the measuring that we will eventually see on the mass spectrum. So it's this detector that's going to give me these series of MS lines that we have seen in a previous video. So that is doing the actual measurement. But before it can do that, the positive cation, the molecular ion, has to be created, it has to carry a charge, and it has to zoom down this tunnel until the very end. All right, so with that said, that's kind of where I'm going to stop, and we'll take a look at the quadrupole, which is going to be kind of the next piece in line in the next video.